let us discuss the XOR problem as an example how we can use the nonlinear activation functions to solve the pattern separability problem. That is, we have a 2 class problem and how can we separate the set of points within these 2 classes using nonlinear activation functions. Okay. So, I discussed the basic truth table of the XOR problem in the last lecture. So, this is basically the problem. We have data points, 4 data points 0 0 0 1 1 0 and 1 1, and 0 0 should correspond to a 0, 0 1 should correspond to a 1, 1 0 should correspond to a 1, and a 1 and 1 should correspond to a 0. And clearly this is not linearly separable. So, let us see how we can tackle this problem. So, what we do is we start with a hidden layer comprising of 2 neurons, and we start with weights, synaptic weights that connect the inputs to the hidden neurons, and they are fully connected, and then we have synaptic weights that connect the hidden neurons to the output neuron. So, neuron 3 here is my output neuron, neuron 2 and neuron 1 are my hidden neurons, and x1 and x2 are my inputs. Okay. So, this is my input layer, this is my hidden layer in the middle, and then I have my output layer. To make things simple, I initialize all the synaptic weights that connect the inputs to the hidden neurons to be 1. So, just observe this carefully. All the weights that connect the inputs to the hidden neurons are initialized to +1. We need to have 2 biases, and I will choose bias B1 to be -½ for neuron 1 and bias B2 to be -1.5 for neuron 2. Let us see how this works. Okay. So, let us consider the hidden neuron 1. So, let us focus on this diagram here on the right hand side. So, I have a sketch of the points x1 and x2. Now, I need to have an activation function for the neurons, and I assume this to be a Heaviside function given by phi of x to be 1 for x to be greater than 0 and 0 else. So, for value of x which is equal to 0, it is 0, and if it is negative it is default 0, and if it is positive it is 1. Now, let us delve slightly into the details. Now, we have these 4 points here, right. Now, at this node, that is for neuron 1, I have x1 times +1 and x2 times +1, and it is going to be summed, and then I have to have this bias -0.5, and then I do the Heaviside function there. So, it is going to be x1 plus x2 minus 0.5, and phi of this x1 plus x2 minus 0.5, if it is positive, if it is greater than 0 it is 1, otherwise it is 0. So, this is the meaning of this equation here, right. So, pay attention to this boxed equation that I have here, which is x1 plus x2 minus 0.5. If it is greater than 0 it is 1, if it is less than or equal to 0 it is 0. Similarly, for the neuron 2, which is the hidden neuron, I have x1 which is scaled by plus 1, I have x2 that is scaled by plus 1, and I have a bias which is minus 1.5. So, I take x1 plus x2 minus 1.5 and I apply a Heaviside function on this. So, this is given by this boxed item that I have here, and phi of x1 plus x2 minus 1.5 is evaluated, and if this result is positive it becomes a 1, it is 0 otherwise. And these can be visualized through hyperplanes, right. I just have to sketch x1 plus x2 minus 0.5 and x1 plus x2 minus 1.5, and for the first case it is a hyperplane like this, and in the second case it is a hyperplane like this. Okay. And then if you carefully observe, the first hyperplane gives a 0, or it separates the point 0 0 with other points. That means it is giving a result 0 for the data point 0 comma 0, and for all the other data points it is going to be 1. Similarly, if you think about the hidden neuron, for the data point 1 comma 1 it gives you an output which is plus 1, and for all the other data points it gives a value which is 0. Now you may wonder, how can I get another neuron that fuses the outputs of the hidden neuron 1 and hidden neuron 2. So, for this what we do is we take the functional signals y1 and y2 from neurons 1 and 2 respectively, and then we have the synaptic weights that connect these hidden neurons to the output neuron, and there is also a bias on the output neuron, and we combine them in some way that we can get the desired result that we want. So, what I do is the following. So, I combine these two hyperplanes, that is from the output of neuron 1 and neuron 2. So, what I get is this activation function, right, activation function which acts on the local receptor field, which is y1 scaled by plus 1 and y2 scaled by minus 1. So, I sum that up, I have a bias minus 0.5, and then when I do the activation on this local receptor field, which is y1 minus y2 minus 0.5. So, I get the output 1 for data points 1 comma 0 and 0 comma 1, and for the other two data points I get 0. So, this is cleverly combined, and carefully observe the negative sign that I have here. Okay. Now, this gives us a sort of a feel how we can sort of build networks that solve higher variable XOR problems, that is multivariable XOR problem, right. So, the goal would be to start with synapses between inputs and the hidden neurons, and for the sake of simplicity we assume them to be all plus 1, and then cleverly we adjust the synaptic weights between the hidden layer and the output neuron in such a way that we can get the desired pattern separability, which is not possible otherwise by using perceptrons. Okay. So, we will extend this to the case for the 3 variable problem, and then we will see how that works. Okay, having gotten the intuition for the 2 variable case, let us consider the 3 variable XOR problem. Okay. So, the 3 variable XOR problem is pretty straightforward extension of the 2 variable case. So, we have y which is a Boolean output, which is x1 XOR x2 XOR x3. So, all these x variables x1, x2 and x3 are all Boolean variables. We form a truth table. So, we separate all the odd parities with respect to the even parities, right. For the 3 tuples 0 0 0, 1 0 1, 1 1 0, 0 1 1, we get the output is 0, and for the 3 tuples 0 0 1, 1 0 0, 0 1 0 and 1 1 1, we get the Boolean output 1 corresponding to odd parity. So, this is the classification problem. All those which are even parity should be a certain class, and all those that are odd parity should be another class. Now, it would be helpful if we can sketch the points in the 3 dimensional space, right. This is a sketch in the 3D space. Okay, this is a sketch in the 3D space. Now, I put the points in this 3D space. All the x corresponds to odd parity and all the circles correspond to even parity. So, I will make it bold circle corresponding to these points. So, clearly we can see this is a nonlinear separable problem, that is, there is no single plane that can shatter the 2 classes, right. So, the 2 variable case we were not able to solve it using a single hyperplane. Similarly, for the 3 variable case I do not think we will be able to solve this. Now, let us see how neural networks can help us. So, our intuition from the 2 variable case sort of indicates to us that we will need a hidden layer of neurons and then somehow fuse the outputs from the hidden layer to the output neuron in such a way that we can solve the parity problem. Since there are only 2 classes, our intuition also tells us that if we carefully combine the outputs from the hidden neurons, just with one output neuron I should be able to realize the pattern separability problem. Okay, this is the intuition. Let us see how we will attack this problem. So, let us build a neuron that responds when at least one of the inputs is a 1. That means variable x1 can be a 1, variable x1 and x2 can be 1, variable x1, x2, x3 can be 1, right. At least one of the inputs should be 1 or more. So, we will start with this signal flow graph. I have inputs x1, x2 and x3. Corresponding to these inputs, I have synaptic weights that connect these inputs to the hidden neuron H1. Okay. So, I go with a simple model, therefore, I have all the synaptic weights to be initialized to 1. So, this weight vector is 1 1 1. Now, the output of this neuron is given by phi of W transpose x plus bias, and W is 1 comma 1 comma 1, x is any Boolean 3 tuple, right. So, you can think of all binary strings of length 3 that are Boolean. So, this is what x is, and I have my bias set to -half, and we will follow the same nonlinear activation that I started off with in the 2 variable case, and that is the Heaviside function. So, let us see how this works. So, if I have 0 0 0, if I take W transpose x, it is going to be 0 and the bias is -half, it is negative. So, therefore, it pulls to 0, the output is 0, and if at least one of them is a 1. So, that means let us assume x1 is 1. So, suppose x1 is 1 and then x2 is 0 and x3 is 0. You can interchange in whichever order you want. You can have x2 to be 1 and rest zeros, or x3 to be 1 and other variables to 0, it does not matter. So, if you consider this case, then I have a 1, x1 is 1 times the synaptic weight which is 1, I multiply 1 times 1 is 1 and the rest are 0. So, 1 minus half gives me something positive which is plus half, and then the activation function will give an output 1. So, you can clearly see that y1 as a function of this tuple 1 1 0 gives me the value 1, right, and you can verify for the other cases. Now, we have gotten a feel. Now, our goal would be to start with a neuron that responds to at least one of the inputs to be a 1, then we will complicate this to construct a neuron that responds when at least 2 of the inputs are 1, so on and so forth, and in the process we get a feel how to get the required function signals that we want, right. Now, let us start building a neuron that activates when at least 2 inputs are 1. That means we can have at least we can have 2 inputs that are 1, we can have 3 inputs that are 1. So, these are the 2 possible cases, right. So, the neuron would respond to at least 2 inputs. Now, let us see how we can adjust the bias. This is very important. The weights are the same, but except if I can control the bias in a clever way, I can make this neuron respond to what it is supposed to do, right. In this case, we have to make it respond to more than 2 inputs being 1, which is greater than or equal to 2 inputs. Okay. Now, let us see this signal flow graph here. We have x1, x2 and x3, these are my inputs like earlier. I have the synaptic weights which are 1 1 1, but what I do is I adjust the bias slightly carefully. In the previous case, when I wanted at least one of the inputs to be 1, I had a bias of minus 0.5. Here I adjust the bias to be minus 1.5, right. So, my output is y2, which is phi of W transpose x plus bias B2. I fix bias B2 to be minus 1.5. Let us work the cases here. Now, when I have the 3 tuple x1, x2, x3 to be 0 1 1, right, my output for this tuple, I need another brace here. Okay. So, y2 corresponding to this tuple 0 1 1 would be 1. Why? Because I have a 0 1 1, 0 times 1 plus 1 times 1 plus 1 times 1, this gives me 2 here. 2 minus 1.5 is going to be positive, which is 0.5, and the activation function will give me a 1, and you can do this for the case when all of them are 1. And just as a cross check, let us do the case when x2 is set to 1 and the other variables are 0, that is I take the tuple 0 1 0, and you can easily do the math because the only variable that I have here which is 1 is x2, 1 times 1 is 1, others will be 0, and 1 minus 1.5 is negative, and therefore, the value is going to be 0, okay. And this is sort of straightforward. Now, with this intuition, if I were to consider building a neuron that responds when all the 3 inputs are 1, you can easily guess that your bias should be incremented by 1 from your previous case, right. So, our bias is going to be minus 2.5. Same idea, the functional signal y3 is the activation function over the local receptor field, which is W transpose x plus bias, and this bias is chosen to be minus 2.5, and let us verify this. When x equals 1 1 1, the tuple is 1 comma 1 comma 1, then we can get the signal to be 3 as a result of the dot product of the input with the weight, and then I add the bias minus 2.5, I have 3 minus 2.5 which is positive, and I get a 1, and you can easily verify for the rest of the outputs I have a 0, okay. So, for rest of the inputs I have an output which is 0. Okay, this is straightforward. Now, what we want is to build the full network with connections to the output neuron. Now, what we have to do is we need to connect the function signals from the hidden neurons to the output neuron. Let us see how we can do this. So, we have 3 synaptic weights that connect the function signals y1, y2 and y3 from the hidden neurons to the output neuron. So, the synaptic weights are carefully chosen, because we have solved for the synaptic weights between the input and the hidden layer. We have tackled that. All we have to do is adjust the synaptic weights in the layer that connects from the hidden neuron, from the hidden layer to the output neuron. In this case, it is a single output neuron, because it is a binary classification problem. Now, so I have a situation where the hidden neuron H1 corresponds to the case when it is greater than or equal to 1 inputs are active. Hidden neuron H2 corresponds to the case when at least 2 inputs are active, and hidden neuron H3 corresponds to the case when all the 3 inputs are active. Now, if I form a 3 tuple from the outputs of the hidden neurons, that is, if I have a neuron which responds to at least 1 input that is active and the other 2 neurons do not respond, then I need to turn this output neuron to respond to a value 1, because it is an odd parity. So, I need to have a synaptic weight which is +1 connecting the hidden neuron 1 and the output. So, if you have the case when H1 so H3 equals 1 implies default that H2 equals 1 and H1 equals to 1, because if all the 3 inputs are active, then definitely we have at least 1 which is active and at least 2 that is active, right. Now, if I do not want the even parity, right, the neuron which responds to at least 2 inputs, that has to be shut off. So, if I want to have all the 3 inputs to be active, right, then this neuron, so what I have to do is balance out the functional signals that I have with at least 1 and at least 2 case to sort of balance them out. So, what I do is put a negative sign to the synaptic weight that connects the hidden neuron H2 with the output. So, I have a synaptic weight which is -1, and then the synaptic weight is +1 for the hidden neuron H3 connecting output neuron which is O1. Now, writing down the equations, the signal at the output neuron is basically phi of y transpose W plus bias, and I choose the bias to be -12, and my functional signal is y1, y2 and y3, which correspond to the outputs of the hidden neurons, and my weights are cleverly initialized to 1, -1 and a +1, and you can verify the truth table and you can see that you get a 1 when there is odd parity and you get a 0 when it is even parity. And the trick is basically by balancing the sign from the neuron where it is responding to more than 2 inputs that are active. Okay. So, with this picture in mind, we can extend this network for a general n variable XOR problem, and this is left as an exercise to the student or the reader to kind of figure this out. So, this is pretty straightforward. You may also wonder why I chose this particular architecture and this particular example, and I did not realize a 3 variable XOR problem via a 2 variable case, right. One can think about a 2 variable case to be, I have a 2 input XOR gate and I can have another input and I can realize a 3 variable XOR like this. So, and if I can have a neural network that can do this, I can have another neural network that corresponds to these outputs, and you can do this in a cascade way as well. But realize that if you did in this cascade way, you will land up with having slightly more number of neurons than what you would have in the example that I presented, and this is a sort of an optimal architecture. Okay. So, and that is the reason why we have considered the case by having just 3 hidden neurons and 1 output neuron, we can realize the 3 variable XOR problem. Okay. So, we will stop here and we will move on with the next module in the next lecture. Thank you.